Professor Paul is a professor in the Department of Computer Science and Engineering in the Indian Institute of Technology, Kharagpur since 1989. He obtained BTech honors in 1983 and MTech in 86, both in computer science also from IIT Kharagpur, and PhD from Indian Institute of Science, Bangalore in 1991. His research interests are computational and combinatorial geometry, design and analysis of algorithms, computational complexity, quantum information and computation. He is a member of the Council of Indian Association for Research in Computing Sciences and convener of Advisory Committee, Center for Theoretical Studies, IIT Kharagpur. He won the prestigious Rajiv Gandhi Research Grant for Innovative Ideas in Science and Technology at JNCASR in Bangalore in 1993. Professor Pal will be speaking on the communication complexity of certain hypergraph vertex coloring games.
This work is on certain hypergraph vertex coloring problems. So I'll be introducing the notation about graphs and hypergraphs. This work is jointly with Rahul Gokhale, who is my master's student. The motivation for this problem is from something in quantum theory, which I admit I understand very little. And there are also some problems which come up in quantum theory or quantum related games, which we want to investigate in the extended versions we have proposed. But the problem is that sometimes you may believe that quantum methods might help in simplifying or solving problems faster, but in many cases it will turn out that their problems remain equally hard. So quantum computing cannot do much for those problems. So that is open for some of our, for many of our problems. But we will mention Cochin-Specker sets because it is from there we started this problem. So Cochin-Specker sets help you in getting what is known as deterministic quantum correlations, in contrast to the normal Bell inequality violation. So one example which is now quite well known is this example of these 9 equations with 18 variables, and it is possible to, what is interesting is it's possible to assign vectors to these variables, vectors in 4-dimensional space. So there are 18 vectors you can assign, so that this set of equations can be solved contextually, in the sense that as such there is no solution to this set of equations, because on the right hand side you have 9 ones, and here you have each vector appearing in 2 equations. 15 appears in 2 places and so on. So it's all even numbers on the left hand side if you assign only zeros and ones to the variables. So if you assign only zeros and ones to these variables, this system does not have a solution. You can't have a simultaneous solution for this set of equations. But if you want to solve it in context, where you give one equation and try to make an assignment that satisfies that equation alone, then it's possible to solve this system, in the sense that you give only one set and then ask for an assignment. Then it will turn out that for x15, for instance, you have to make 2 different values when you ask for this system and when you ask for the other system. So there are ways of working it out. Because it's not possible to identify what you must assign to a particular variable, say 15, whether you should assign it 0 or 1, and because you need to assign either a 0 or 1 based on the equation which is given to you, you might therefore require the context to be conveyed, just in case you play it as a game. Imagine that you are giving the equation to one party called Alice and the variable to another party. For instance, if you look at the last equation, suppose you give this equation to Alice, and Alice has to assign exactly 1 1 and 3 zeros, so it can assign 1 to any one of these 4 and zeros to the rest. But Bob is given exactly one of these 4 variables, either x15 or x13 or x18 or x17, and Alice doesn't know which variable Bob is given, and Bob doesn't know which of these 2 equations containing x15 is given to Alice. So both don't know something about the other party. So, but they all know this set of equations. So they have the knowledge that x15 appears only in 2 equations. And Alice knows, given the equation, that it is one of those 4 variables which is given to Bob. So there is this kind of promise in the inputs which is guaranteed. So there is no confusion about that. They know what they're going to do, but Bob has to decide which equation. Now, it turns out that Alice has to tell Bob which equation it is, and then they can fix out a strategy of coloring, of giving ones and zeros to the variables. For example, if it's the 6th equation, then Alice will assign a 1 to x15, and if it's a 9th equation, then Bob will convey, okay, now you assign a 0 to x15. So based on the equation which Alice gets, Alice will dominate and communicate to Bob as to which value is to be assigned. So this is roughly the scenario, and therefore you need communication to be done because the context is important. So the context is converted into communication. So we are interested in the communication complexity of certain games of this kind, where a big set is given to Alice and one element of that set is given to Bob, and both Alice and Bob have to give 0, 1 values to all the elements of the set. Bob has only 1 element, and Alice has the 4 elements, as you can see here. And they must win in the sense that Alice and Bob should assign the same value to the common variable. So that's called winning, and they have to always win for whichever equation you give and whichever variable you give there. So this will become more clear as we proceed. Okay. So ignore everything except, okay, let me go to the next one. So what is the hypergraph here? The hypergraph is something like this. You take this set of 3 vertices. I'll explain some terminology because some of you might not be using the same terms for the things. Now these are entities. These circles are called vertices, vertex, V-E-R-T-X in computer science literature. These are like nodes of a network, or these are like agents or elements which are across and then these edges connect them. So this is called a K2-3 because there are 3 vertices and pairs of 2 making the edges. So there are 3 pairs possible, 1, 2, 2, 3, 3, 1. And in this case, there is another graph, hypergraph. Now this hypergraph is more complicated. There are 4 vertices, no doubt, but every group of 3 vertices forms the hyper edges, or edges you may call. For instance, 1, 2, 3 is a subset of all the 4 elements which forms a hyper edge. Then 1, 2, 4 is another hyper edge. 1, 4, 3, it's like a pyramid. So 1, 4, 3 is another hyper edge. All the faces of this pyramid, the triangles, are hyper edges. Hyper edges of cardinality 3. So this is called K3-4. It's also called the complete hypergraph of 4 vertices taken 3 vertices at a time. So this kind of things you find in combinatorics literature in hypergraph theory. So these are called graphs. So graphs are entities connected by relations. Relations can be either pairs or triples, or again triples here. Now here there are 5 vertices, but this is something I didn't draw here, but you can imagine there are 5 agents and you take every group of 3. So 5C3 will be 10, 5 combinations 3 will be 10 sets of 3 vertices will form the hyper edges in this case. So this is the notion of a hypergraph, and this is the game, hypergraph vertex coloring game. So you have to give inputs to Alice and Bob, and the inputs are not known to each other. Alice knows its own input, which is a hyper edge H, and a vertex is given to Bob. So, for instance, in this case, if I play the game with K34, I will be giving maybe say 2, 4, 3, this hyper edge, 2, 4, 3 hyper edge to Alice, and maybe I'll give 2 or 4 or 3, one of the vertices to Bob. So Alice doesn't know which vertex is given to Bob, and Bob doesn't know, even if Bob is given the vertex 4, it doesn't know whether this hyper edge or this, which one of the hyper edges containing 4 is given to Alice. So they have to color the vertex 4, for instance, both white or both black. That is 1 or 0, and then they win. So that's what they have to do, and for that purpose they can communicate with each other. This is the problem. So classically speaking, if you want to solve this problem, is what we are mostly investigating, and there you need to communicate from Alice to Bob. And in particular, we'll be considering only the cases where Alice communicates and only Alice communicates. So Bob doesn't do any communication. Bob just receives the information and takes a decision about coloring. So for every pair of inputs possible for Alice and Bob, the vertex V, which is there in the hyper edge H, should be colored the same way in both. So Bob has to get enough information about it, because the vertex can appear in number of hyper edges. And Alice also doesn't know which vertex has been given to Bob. So this I'm just repeating because we need to do initial understanding of the notation. Well, control L, right? Now, in this case, there are quantum solutions with zero communication using entanglement, but I will just tell you the so for this set of equations, there is a quantum solution with zero communication if you use a priori entanglement, and that goes as follows. It is possible for you to assign some vectors from the 4-dimensional space. Now these are the 4 basis elements, so these are the coefficients of the 4 basis elements, and so these vectors are the 18 vectors. If you make this assignment, there is a lot of symmetry which is apparent here, but if you make these assignments, then as per the equations here, each equation will represent one orthonormal basis with respect to those vectors. So these are the 9 bases which will be realized if you have these vector assignments, and using a certain entanglement, which is an extension of the Bell state, you can solve this problem. Classically speaking, in the 6th and the 9th basis, as I told you, one vector has to be assigned 1 in one case and 0 in the other case. So assignments of 1s and 0s to these vectors or to these variables x1, x2 is what you view in the classical domain, but in the quantum domain you can view them as if you are solving it through these vectors, through those bases, and using an entanglement to do some measurement so that you get the same results at both Alice and Bob's places, and therefore you can do the consistent coloring. So it turns out that this entanglement is useful, which is like the 0, 0, 1, 1. So this is a 4-dimensional state. So if you take the 4 basis vectors, then this is the entanglement which works. So I'll just mention a few points here without going to the details. So it turns out that using this entanglement, it will always be possible to ensure that as long as there may be 2 sets of equations and therefore 2 different bases which share a common vector which Bob gets. So Bob will get something, but it doesn't know whether it belongs to this basis or this basis. But in that case, if Alice does a measurement in the first basis and Bob does a measurement in either of these bases, still both of them get the same answer. So they can't get different answers. They can't get different answers. So that's how you can work out with this entanglement, because the probability of xc and xc prime being different is 0. So this is a rough calculation for that. But you don't have to bother so much about this, because we are only going to look at other variants of the problem, where we will not be dealing with such nice examples like you saw here. Rather, we'll deal with very nasty cases where there are too many hyper edges and too many equations actually for a very small number of vertices. So we are trying to make the problem essentially more complicated, but there are reasons for it. Like you have seen that at least in this case, F5. Okay. No, F5 doesn't work. Okay. No, not this one, the other one. So yeah, this is good. So in this case, you can see now I have got the idea. Here you had a set of equations which had only nine hyper edges. So if you consider a hypergraph of 18 vertices, all these 18 vertices, then we had only 9 hyper edges. It's a very sparse graph, and therefore possibly you could map it into Cauchy-Specker set and had a quantum solution with 0 communication and so on. But we will create games where you have many more hyper edges given and make the problem more in some sense complicated or nasty, so that we don't know whether a quantum solution is there for this new problem, which is also quite hard in the classical case. Now it turns out that this problem, this quantum problem, which is solved with zero communication cost just by a priori entanglement and some measurement in the quantum case, can be solved with exactly 1-bit communication, where the context of one common variable between two equations has to be conveyed. So you need only 1 bit to tell either 0 or the first one or the second one. So you need only 1-bit communication. But the problems we are constructing have very high communication complexity. Now there is a naive approach here. I don't know whether it's valid. We are trying to boost up the classical communication complexity to see whether the same problems can be solved with somewhat lesser quantum entanglement, somewhat lesser communication using quantum entanglement. But it might be the case that you cannot make an improvement. So we don't have much idea about that. But at the same time, we try to construct games where you have very high classical communication complexity. So in that context, I will go back to our new game and explain what we are doing there precisely. So now forget about Cauchy-Specker sets for the time being and just consider this game. So what I'll give to Alice is either 1, 2 or 2, 3 or 3, 1, and one of the vertices to Bob. And you can see that if I give the vertex 1 to Alice, any edge containing vertex 1, which is either this or this, then there can be an agreement or a strategy between both, that as long as the vertex 1 is present, that is, it is one of these two edges, both will color the vertex 1 as white and the other vertex is black. So then there is no problem, as long as Alice can tell Bob, use this rule, I have got a vertex 1. So then they can come up with a winning situation. So vertex V1 will be colored white, and either V2 or V3 which comes will be colored black. So as long as it is one of these two edges, there is no problem. But then if the next edge comes, then this doesn't occur anyway. So they will be both coloring V2 as white and V3 as black. So this is the strategy they use. So there are two strategies. So Alice tells Bob 0 or 1, meaning that either use first strategy or second strategy, and so the game can be won. So there are two strategies possible. The combination complexity is therefore logarithm of 2, which is 1 bit, because 1 bit is sufficient to convey which one to choose. Similarly, in this case, it's a very similar situation. 1 bit is again sufficient. You can see that there are 4 possible hyper edges, and as long as vertex 1 is there, it can cover 3 hyper edges. So in that case, you can color vertex 1 as white and anything else as black. And if the last one comes in, then you can color maybe V2 as white and others as black. So there is always a coloring strategy. Both can do the coloring and win the game. So you can see that as long as this number is 1 less than this one, there's only 1 bit sufficient. In fact, if you had K43 instead of K45 instead of K35, you still do with 1 bit communication complexity, because you can see these pyramids are always, when you have one vertex red, it covers up the rest, and then only one edge remains. So in this case, an edge of 2 vertices remains. In this case, a hyper edge of 3 vertices remains. So it's quite generalizable to K3, 4 and K4, 5 and so on, K6, 7 and so on. In general, Km, m plus 1. You need only 1 bit to do. So this is a very powerful protocol. But for K3, 5, you need a little bit more of strategies. So I'll just explain these strategies because we'll need them later on. So as long as vertex 1 is there in, you color it white, and then you may see that, okay, vertex 1 is not there, then vertex 2 is given priority. So anything else coming is dark. Vertex 1 is not there. And if both of them are not there, then you only have this possible edge, because all edges with vertex 1 and vertex 2 have been already covered. So you have only 3 strategies which can help you do the proper coloring and win the game. So whichever hyper edge of 3 vertices you put, if V1 is there, then you do this strategy. If V2 is there, you do this strategy. And if none of them are there, then you do this strategy. And that's only one hyper edge left. So you can get done with 3 strategies. And therefore, Alice has to send 2 bits to Bob, telling whether it's the first, second, or third strategy to be used. 2 bits are sufficient. So the communication complexity is 2 bits. So this is essentially the main idea of the protocols we have. So it's now easy for us to see that as long as you have a complete set of strategies where you can account for every hyper edge. So here you have every hyper edge involved. So for every hyper edge, if you have some strategy which can cover it, the whole graph is covered, and therefore the game is won for every possible input to Alice and Bob. So in fact, you saw here that all the edges are covered. Hyper edges with V1 are covered in the first rule in all these cases. Hyper edges with V2 in the second rule, and so on. So this is a very neat strategy, and you can work it out. So the only part of this is that if the hypergraph vertex coloring game is 1 for every pair, then there is a solutions that is a set of functions as we did here. These are called strategies. So and the whole thing is called a solution. So these 3 strategies make this whole solution. So as long as you can win for every input pair, you can then work out a function for each hyper edge, and therefore you can have a set of functions. So for each hyper edge you can have a function, and so you have a set of functions giving us complete solution. So you have a solution of strategies if and only if the vertex covering game is 1 for every hyper edge. So this lemma is in some sense fairly tautological, and just to tell you what is a complete solution is a set of strategies, and the set of strategies helps you to win the game, and the number of bits to be communicated is logarithm of the number of strategies in the solution set. Now, here are a few simple observations about the strategies. So this is a summarized theorem. If S is a solution to the hypergraph G, then you need log of S amount of communication provided Alice alone communicates to win the game for every input pair to Alice and Bob. So that's the initial result, and then we can define what are known as consistent strategies. So 2 strategies are sort of compatible or consistent if we don't put a we don't assign anything in one of them. Or if they are same for some vertex. So you can see that in the strategies we had here, for every value of v, we had a w. So f of v1 is w, f of v2 is b, and so on. So 3 functions are defined, mapping vertices to w, b, and dash. So these dashes are like you don't do any mapping. So they are not really like don't cares, but they are like nothing is done. That assignment doesn't exist. So either you have a w or a b or a minus or a dash, and that is the function. So we have 3 valued function for over the set of vertices, coloring either black or white or not assigning any coloring. So if you have 2 different strategies which assign the same color to a vertex v, or one of them is not assigning anything, then you can merge the 2 strategies. So merging can be done as follows. You can assign it to f1v, f2v is sort of silent, otherwise you can make it f2v. And this is a small simple result telling that if f1 and f2 strategies satisfy strategies satisfy different subsets of the whole set of hyper edges, then the merge strategy satisfies the entire set, the union of the 2. So, but this may not be very useful for us. But to tell you a little bit more about these strategies, we'll take a look at this K24. K24 has a nice strategy where you can use a strategy v1, v2, and v3, v4, which these arrows mean that v1 is white and v2 is black. So this second strategy does coloring for v1, v2, and this one does it for v3, v4. So other edges are not covered by these 2, and for instance, the edges v3, v2 is covered by this set, and so on. But if you merge these 2 strategies, you get a new strategy which looks like this and which covers more edges. So initially we had the first strategy which can be indicated in this manner, that v1 and v2 were both white, so they were dominating on the other 2 as blacks. And we had the other 2, f2 was this and f3 was this. So you had this set of strategies in the beginning, and then we got a merge of f2, f3, and it turns out the merge of f2, f3 with f1 also solves the K24 problem. So this is just to show that merging helps you get finer solutions. So we had a solution with 3 strategies, now we have a solution with only 2 strategies, f1 and f4, where f4 is a merge of f2 and f3. But this is not very important for us now. Now, since we talked about minimizing the number of strategies for winning a certain hypergraph game, so we can talk about the smallest solution, or there may be many smallest solutions. So just take the logarithm of that is a lower bound on the minimum on the communication complexity, because it can be shown that you can have a shorter communication from Alice to Bob, which will help Bob and Alice together resolve the correlation. So the proof goes by showing that if you had a more economical protocol, then you can derive a contradiction. So I'll skip that proof and go over to the other examples where I'll switch back to the other slide now. So just to recap, we are considering complete graphs, complete hypergraphs, and then what we have been doing is vertex coloring game on these complete graphs. And this is in summary what we are doing, that Alice must color exactly one of the vertices as white, and Bob must color the vertex V as black or white, and they win if they give the same colors. And this must be possible for all hyper edges. Then you say that the entire graph is one. That is you have a solution for the entire graph. This is a summary of that. And And I have just explained the cases of K23 and K34, how one bit of communication suffices. So ignore this. Okay. And to recap the definition of coloring strategy, you have a function from the vertex set to 3 possible labels: white, black, and no label, no coloring. And these were the strategies we have used, some of the strategies. So this was a strategy used for K35. So anything containing vertex V1 goes white, otherwise V2 goes white, and lastly V3 goes white. So 2 bits suffice. And so this is the definition of the solution, that a solution is a set of strategies which together satisfy all hyper edges. And just as I told you, you can have various sets of solutions. So these are the 2 solutions for K24. One of them is smaller than the other, and therefore the notion of minimal comes. Now, the minimal solution cannot have a pair of consistent strategies that can be merged to get a smaller set of strategies. Because if this were there, then the merged solution can also solve the problem and you have a smaller solution. So that's the overall idea of the proof, which I skipped earlier. This is a summary of results we have. I'll go to some of the details quickly. Now, R equal to 2 means ordinary graphs where you have 2 vertices connected by edges. So when you have n vertices and pairs of vertices as edges, then you need at least log n to the base 3 bits to be communicated from Alice to Bob, at least so much. You need at least so many bits to be communicated to win the game. Any strategy would need that. So this is a lower bound. These are all classical results, and we can do with log n bound. So there is a gap which we couldn't cover. There is a ratio between these two which we couldn't cover. For the case where you have R1 less than this, I told you that 2 bits are sufficient, or 2 bits are sufficient. In fact, you need an additional bit. So this is optimal, and even when you have n minus 2, 4, that is when you have K35 or K46 or K1012, in those cases 3 bits are sufficient. Now these things can be proved, these are not very difficult. The interesting case is when n is large compared to R. Now remember that this R is the number of vertices in one subset or in one hyperedge. So in ordinary edge there are 2 vertices in graph theory. So when R is say fixed and n blows up, so R is fixed as a constant and n goes to infinity, you need log to the base 3 of n minus r plus 1 bits at least, and we have a exponential gap here. In fact, what I am mentioning here is the number of strategies. So you take a further logarithm, then you get the optimal, you get the number of bits to be communicated. So if you need log n to the base 3 strategies here, you need another log. So log n bits are required and log n bits are sufficient. In this case, a logarithm of this, so log to the base 2 of log to the base 3 of n minus r minus 1, and you need log of n minus r plus 1. So between these two, of course, there is an exponential gap, which we have not yet been able to cover. So this essentially happens because when the number of vertices blows up and becomes large, we don't know exactly how to capture the argument we gave here. Whereas this upper bound, this matches the lower bound. The 2 lower bound proofs are similar even if they are generalizations. This is a generalization of the other one. So this is a summary of the results. I'll go to some technical details of a few of those results. Yeah, so this is the first interesting proof. This is the K2n game. So this is the simplest game. You have every edge has got 2 vertices. Every edge has exactly 2 vertices, and there are n vertices, and you want to play this game. So let S be any solution to this game, and let the number of strategies in the game be m, small m. So there are F1, F2, Fm. so many strategies, each assigning a certain W, B or minus value to a vertex V. So, in particular vertex Vi, and therefore, there are n such m tuples. Now, this is I ranging from 1 through n. So, there are for every vertex V1, V2, V3, you have one such tuple, n tuple. Actually, I have written as a set, but actually it is supposed to be a m tuple. Now, the number of m tuples is 3 power m, and let us assume for the sake of contradiction that the number of strategies is smaller than log to the base 3 of n, in which case we would get a lower complexity than this. This is log to the base 3 of n, and if your strategy is less than this, then you have a bound which is smaller than the lower bound, which is a contradiction. So, what we will try to do is, we will assume that m is less than log to the base 3 of n, which is also equivalently 3 power m is less than small n, and then derive a contradiction using the pigeonhole principle. So, what we do here is, because n is larger than the total number of possibilities, two possibilities out of this 3 power n will repeat for some two vertices. For some two vertices p and q, say Vp and Vq, all the values will be equal. So, you can view it as columns for vertices and rows for the functions. So, the m rows and n columns. So, there are m rows and n columns, and so you can imagine that for every function will be equal for some two vertices, fixed. You fix two vertices, but if that were the case, then those two vertices will be always assigned the same color, either both black or both white in every coloring, which means that they are mutually redundant and you can merge them into one. So, you have a lesser number of strategies. So, there is a contradiction there. So, what goes wrong if you assign the same color to Vp and Vq? Because we have edges of two vertices. So, if you take in particular the edge Vp, Vq, either both of its vertices get colored zeros or both get colored 1, but we do not have the Cochin-Specker kind of thing that exactly one has to be 1 and the other has to be 0. So, we do not have a coloring strategy. So, the idea is that there is a edge Vp, Vq, both of its vertices are either colored zeros or colored 1. It is not the case that any strategy can color them 1, 0 or 0, 1. So, the game fails at least for one edge, and therefore, you cannot win the game. So, the solution that we get, which is of less than which is less than log n to the base 3 strategies, is not a solution, and therefore, we have this lower bound. Right. So, what is nice here is the use of the pigeonhole principle, that we have more vertices than we have codes possible, and therefore, two vertices get the same functions and you can't distinguish between them, and therefore, coloring both of them identically does not help you win the Alice Bob game. The game, we require that the coloring of the vertices, Alice should color at least exactly one vertex 1, other one 0. So, here it colors both as 1 or both as 0. So, that is the problem in this case. And there is another theorem which says that in the case of KRN, which is a generalization, R is not just 2 now, it can be anything, any constant bigger than 2, and then you need log to the base 3 of n minus r plus 1. So, you can ignore the R if you wish, and then take another logarithm. This is the number of bits to be communicated, which means the number of strategies is what is there inside this. So, we assume here that you have a solution which is smaller. So, log to the base 3 of n minus r plus 1, or equivalently 3 power m is less than n minus r plus 1. And then we derive a contradiction that such a solution, which is a smaller cardinality in terms of number of strategies, will not be able to win the game for every hyper edge. So, that is what we need to do. But there is a small supporting lemma which I will skip. So, here what happens is that this is a slightly technical, and I will skip most of this proof, just give you an outline. we define a set D of vertices out of the full set of vertices V, and for which all these function assignment tuples are different. So look at this tuple has got something like m entries for every vertex I going from 1 through n. So if you take one tuple, then there are some m values assigned here, which are w, b, or dash. And if you have another tuple like this and you place below it, if there is a difference in any position, say 1w becomes b or 1b becomes dash or something like that, then you say that the two strings are different or two assignments are different. So D is a set of all those vertices for which these tuples differ somewhere or the other, and they are not totally identical. Like this is, these are different from the next set, somewhere it is different. All of them may be same except one or more than one, but there must be difference in some position out of these m positions. So that is the kind of set D we are defining. Then we define V minus D, which means the set V minus D, set minus D, is the set of all vertices for which the assignments are absolutely identical. The function assignments are absolutely identical. Now, it's possible to show that this is less than, this is of course less than 3 power m because it is a set of vertices, and we have assumed that this is less than n minus r plus 1. So 3 power m is also less than n, and therefore there is another reason to say why D is less than 3 power m. I'll skip the proposition which I proved earlier here, but just assuming that D is less than 3 power n, we get the set of identical vertices, vertices with identical patterns as r minus 1. So this is a small number which is a constant, but you have a bunch of vertices which have absolutely identical patterns, and then we have a selection to choose. D has got at least one vertex, which is easy to see because D can't be empty. There is at least one vertex which has a unique representation. So if it matches with all the others, it is there as 1, and we have r minus 1 here, and it's possible to choose a set of r vertices from this construction, which I am not going to present here, so that the set of r vertices forms a hyper edge which cannot be colored by any suitable strategy. So what happens is this construction will give you a hyper edge with r vertices where any coloring strategy in the set S, as we have assumed, will end up giving same colors to at least 2 vertices. It will give white color to at least 2 vertices. Otherwise, it will give 0 to all. Suppose it gives zeros to all, then it doesn't satisfy your Alice's coloring strategy that there should be at least exactly one vertex white. On the other hand, if there is anything which is not black, that is white, then another one will also be white. So the whites will come in minimum of pairs or triples and so on. So you will be getting a hyper edge which can't be colored, and therefore the solution will fail. And that will fail because of restrictions like this. We assume that 3 power m is less than n minus r minus 1, or the number of strategies possible to win the game is further less than this, and therefore we have this lower bound proof. So there is a technicality here which we can skip, but then what I did earlier for this K2n proof is very neat here with the pigeonhole principle. Okay, so I'll summarize with a little bit more on the upper bounds. I think how much time do I have? Okay. So upper bounds are not very difficult to prove because we just have to show there is a solution. Now just imagine you have n vertices and r subsets, and in contrast to n plus 1 vertices and r subsets, then any solution, if you take a minimum solution for this set and a minimum solution for this set, then naturally the solution set for the bigger graph will be enough for the solution set for the smaller graph, because this solution S prime satisfies a subset H of the bigger set. So a subset satisfies well, if you have a set satisfying the bigger graph, then then there will be the minimum, so you just drop one vertex and you get whatever solutions, minimum set you get will be smaller than this. Okay, so this is a hereditary property, but what is interesting in this one, the solution set, minimum solution set for the larger graph, there is some part of it has not been scanned, is no more than 1 plus the solution set for this. And how to do this? We'll show that if you take the solution set for the smaller graph, then you add a new vertex and just put no assignments for it, for all the strategies of this kind, of the old one, and then you put a new strategy. So all the old strategies are extended by one vertex with a dash, with nothing to assign, and you add an additional strategy for every vertex and make it forcibly black for everything but the last vertex. So that is just like an inductive construction. We saw this for earlier examples, and since you have now got a bigger, you have got a solution set, the minimum of the bigger cardinality will be dominated by this, and therefore it will be less than s plus 1. So you will get this condition because you have a solution strategy which is possibly larger than this, but just one more than what you have here. So these are not difficult to prove, and as a corollary you can see that you can keep building up. You start with a base set of only r vertices, a trivial hypergraph with only r vertices, one single hyper edge, and then you can keep on, then you need only one strategy for it, and you keep on adding one strategy as you keep on adding vertices. So you can add at the most n minus r vertices. So this goes up to n minus r plus 1, one at a time, and the logarithm of that will be the combination complexity. So you have one starting with, and then you have n minus r to add, and then you take a logarithm of that to get the combination complexity. But that is not all the story. These are all for complete graphs, but if you also take hypergraphs, arbitrary hypergraphs which are not complete graphs. So arbitrary hypergraphs can have various kinds of, they may not have many subsets. So it may have a cluster of subsets here and cluster of subsets there. So they are not complete graphs. So all R subsets may not be there. Some R subsets may be there, some R plus 1 subsets may be there. In that case also we can extend our strategy notion and play these games with very similar combination, slightly higher because this R mean comes here. R mean is the minimum number of vertices in a hyper edge. So I'll summarize with a small fun game I played with outside my domain. I played with some of those Cauchy-Specker vectors, and I'm sure some of you may find it somewhat interesting. But this may be a very elementary observation. So what we did here, we added some 4 vectors to the already 18 set we had here. So this just take me 2 minutes. I'll explain what we did here. So you had this initial set of vectors which helps you solve that original Cauchy-Specker game, and there are 18 vectors here. So we added 4 vectors to this set, and it turns out that if you add these 4 vectors, then you can also add 4 bases which will include these vectors, and add 4 bases. So you add 18 plus 4, you get 22 equations now. And they also have similar property that you can play the same kind of Cauchy-Specker game and solve it with 0 communication for upper area entanglement and 1 bit communication complexity for classical case. On the other hand, okay. So the classical strategy would involve now, of course, there are 22 vectors, and then you have similar, you can just subsume this subsumes the same kind of protocol for the classical case. You just have to have context to convey from Alice to Bob with 1 bit, and assignments can be done. So essentially what we did is we applied this operator on the 4-dimensional space of all the 18 vectors. Now, this is not really permissible, but what this is actually x cross x if we x tensor x if we consider the 4-dimensional space as made out of 2 qubits. So if it were made out of 2 qubits, then whatever state you have in the 4 dimensions, if you do this operator, whatever it is called, it is x cross x tensor x, then you get that set of 4 vectors. And then we also tried with z cross z, and we got some new vectors like this, new vectors, but I think we had some 6 vectors in this case. So what happens is the 18 set of vectors gets converted into another 18 set of vectors, and there are some overlaps. So there are some new vectors now. So either 4 new vectors or 6 new vectors come in different cases, and corresponding you can add those vectors help you to add some new basis elements which you can be framed by symmetry of the equations in the original set, and you can get up to 22 equations or 24 equations, and again play the same kind of game, same arguments. And we did it with other operators also and found there can be 6 new equations or something like that. Finally, what I propose is whether we can study more general unitary operations and see if we can get some nice geometry of these sets. But it turns out all the operators we use are self-inverses, but other unitary operators can be considered. Okay, and at the end, I'll just show you what we found out from plotting all these transformations. Yeah, this is what we got. If you do all the poly tensor products like xi, ix, xy, xz, zx, all those 16 combinations, then you can get only these set of vectors, 48 vectors, and you can see the nice symmetry between. Some of them are complex and they may not yield you Cauchy-Specker games with the same kind of entanglement, but nevertheless you have many of them which will help. So you get 48 vectors only in the 4-dimensional case, as we started with the 18 vectors. So with all those 16 operators, you get only 48 vectors, and of course the bases get transformed so that there are a lot of overlaps and some new vectors each time. And this is a map, so this should be xi. So you have all these 16 operators, and these are the original 18 vectors, whatever they may be. I've just numbered them, and if you do these various operators, then these are the new vectors that you get. From the first vector you get these, from the second, third you get this. So you can check that x tensor x will come from 1 to 2 to this, so you get 19. These are the two 19s. So you can check that. So you get these 18 vectors transformed in this manner. I was just trying to see if this makes any sense. But if you take Cauchy-Specker sets in the other dimensions, 3 dimensions or higher dimensions, it might be worthwhile studying some algebra or some geometry of these set of bases, how many bases you can form, how much is overlap between the bases. You may try to see if any correlations or any, you can have higher amount of context to be played, so that you can get more costly classical games, whereas the quantum games will be 0 communication complexity. So those are some of the questions which may come out from there. So that's what I wanted to say. So in summary, what we have done is we have essentially looked at some kinds of games which come from Cauchy-Specker games, and they're motivated by Cauchy-Specker games, and for which we have interesting lower bounds of double log. What remains open is, as I showed you the table, if you look at only the classical results, then certainly these are the open problems. These are the open. This is the huge gap which is open, and this proof is somewhat an extension of this, but a little bit more complicated. So the communication complexity is just a logarithm of all these numbers. This is just the number of strategies in those solutions. Thank you. I'll conclude my talk.
Thank you very much.